Hello everybody, welcome to the third part of the embedded system course which is on testing. Today we will start the third unit of this part on testing, that is actually testing for advances in testing for embedded system hardware. In the last two basically parts of the testing unit, what we have seen first what are the basics of testing, and then we have seen some of the specific testing concepts which are mainly applicable for embedded systems. Now in this part what we will be mainly looking, as you can see in the course plan, it is on advances in embedded system technology. That is, with this more becoming sophistication of the digital hardware and more typical kind of constraints which is coming into embedded system design, like meeting the timing constraints, meeting the power constraints, etc. So what are the different advanced test techniques that are required for such cases? So as we see, we will first see what are the different fault models which required to verify the real time operation correctness. Secondly, we will be looking at built-in self-test, and then after that we will give two dedicated lectures for fault tolerance of embedded systems. So these things are mainly required in the modern technology, circuits which are built using the modern technology and which are applicable for a large class of embedded systems where we require fault tolerance, where we require real-time guarantee, etc., etc. So the first lecture on this is testing of advanced fault models in real-time embedded systems. So whenever we talk about embedded systems, nowadays the term called real-time is becoming very important. What do you mean by real-time? As already discussed in details by Arnab Sarkar sir and Professor Deka, that basically whenever we say embedded system, we have some kind of deadline boundaries. That is, all the operations not only have to be functionally correct, but also they have to be temporally correct. That means you have to generate the correct solutions and at the correct time. That means you should meet the deadline. Also, we have talked about hard deadlines and soft deadlines. So hard deadlines are mainly for mission critical applications like a car, avionics. Then you can tell about the nuclear reaction chamber. Everywhere there are embedded systems. So there you cannot at all delay the answers by which time it should be ready. That is, not only correctness, but absolutely before the deadline it should be made. There is something called software deadline systems like a microwave controller, a washing machine controller, where you can slightly delay the answers by which the delay the deadline by which the answer should be ready. But mainly when you are talking about testing, today we are mainly concentrating on the mission critical applications, because there it is very important that you do not miss the deadline. If you do that, there is a lot of catastrophic problems that can happen. Like for example, you are applying a brake in a ABS vehicle. Then basically, if the brake should be applied in a particular deadline after you press the brake shoe, if it misses the deadline, there can be an accident. So you have to be very careful about the missing of the deadlines. So we'll look at that in this lecture. So we have already seen in the first unit of this testing part that structural testing with fault models, that is the stacked fault models, is the de facto standard. So what we have seen, that we are testing the circuit structure in it with fault models which involves verifying each unit, that is gate and flip flops, is free of faults from that fault model. And generally we talk about stacked fault. So what we have seen, rather than testing the functionality of the circuit, we have tried to verify that none of the gates or none of the flip flops have a stacked zero fault. So we have discussed this in details. So what is a fault model? So fault model is an abstraction of the real defects. And why we do that? Because they are really easy to represent, automatic test pattern generation becomes simpler, and there are less number of test patterns to test those circuits, so test time gets reduced. So we have seen that stacked fault model for this purpose serves a very nice job in that manner. But there is a problem. So stacked fault model, if you have seen, that it tells that whether this line is stacked 0 or not, and we actually verify that none of the line is either stacked 0 or stacked 1. Similarly, we do it for all. But it guarantees that if you can find out that a circuit does not have any stacked fault, then generally it is 99.9% accurate. The circuit does not have any kind of functional defects. Functional meaning correctness of the answer. That is, if I apply 1 1, you will get the answer 1 1. If you get 0 0 0 1 0 or 0 1, you will always get the answer as a 0. So that is the functional correctness I can guarantee. But what about delay? Say you know that in real time systems, what do you mean? Real time system means basically you have a black box and some inputs are coming to it, and the output should be ready by a particular deadline. So our answer should be ready by a particular deadline means your hardware, after taking the input, should give you the output with a specific deadline. It should not miss any of the deadlines. That means your circuit should operate at the same frequency which you are expecting it to work. So I think you can easily understand Stacked fault will not serve the purpose. Stacked fault model will tell you that given a very large amount of time, you will always guarantee that the output functionality is correct. But it just states that none of the line is Stacked 0 or Stacked 1. That is, it is behaving properly as per logic 0 and 1. But time taken it does not verify. Therefore, to verify the temporal correctness, or that it will definitely guarantee to meet all the deadlines, it is very, very important that we should have another different kind of fault model, which we call as the basically your delay fault model. So what is the delay fault model? Delay fault model will just tell you not only that if you apply a 0 0, the answer will be 0. Not only the answer will be 0, but also it will be delivered at the proper time. Like for example, you have 1 1, the answer will be 1. You transit it from 0 to 0 0, then it will guarantee that this transit from 1 to 0 will be within a particular deadline, which is the delay of the gate. And as you know that a circuit will be something like there are a lot of gates in chain. So if you assure that all the gates are meeting their deadlines, or they will deliver the results in deadline, then you can totally ensure that the circuit will also give the final answer within a deadline. So that will allow that not only your devices will be functionally proper, but at the same time they will meet your delay and deadline, your deadline constraints. So that is the idea. So what are the delay fault model? As I told you, just like Stacked fault model, you cannot just like the motivation of Stacked fault model, you cannot think of just testing for all the gates, whether it will rise properly, whether it will fall properly, and so much transient delay. All these things is not possible to measure and test because of the huge amount of time that will be required. So what we will do, basically just like Stacked fault model, there is something called delay fault model, which will take lumped delay of the gates, whether, so you can understand that delay can be within the gates or delay can also be with the interconnects. So if you start thinking about all this, because the interconnect is nothing but an RC line, generally sometimes people call LRC or RC lines, the resistive, capacitive and inductive lines. So basically if you try to model all these resistance, capacitance, inductance, then find out the transmission line properties, then it will actually lead up into a very bad situation where it will take large amount of time to test it. Like the delay of a line depends on its capacitance, it is parasitic capacitance, inductance, resistance. So when we start designing a circuit, we sometimes assume a lumped delay model, or sometimes assume that there is no delay. But as in the case of Stacked fault model, if you start testing about what is the parasitic capacitance, what is the delay because of that, you will land into a big problem, because we will have no time to test such rigorously, and not required also. So just like the Stacked fault model, people also have tried to think that I will consider delay is lumped within the gate, that if the gate can delay, if the gate can deliver the answer in a proper manner, in a proper amount of time, then we assume that it is correct. That is, the delay of these lines and the gates and all the transistors etc. are lumped into the gate delay itself. That is a model like a Stacked fault. I will go into more elaboration, then we will get the concept. For the time being, it is just enough for you to understand that instead of considering all sorts of physical delays involved in a gate, transistors and the lines, we lump it to a gate and assume that there will be no delay to rise and no delay to fall. I mean, that is mean the output means if you want to go from 0 to 1, this rise will be within the proper deadline, and if some value has to fall, it will fall within the required deadline, which is assumed deadline for the gate. So if it happens properly, you can take care that the delay of the gate as well as the delay of the interconnects are taken into picture. So just like a Stacked fault model, instead of looking for all kind of physical defects, we assume that none of the gates lines have a Stacked 0 or Stacked 1. So here in this case, we try to verify that none of the gates will have a delay to rise or delay to fall. That is what is the idea of a delay fault model. So if you look at it, that is the input output of a gate have delay to rise or delay to fall. If none of the input lines or output lines have delay to rise and delay to fault, then we can assume that the circuit will be giving a solution in the real time, meeting the deadline. And it has been found that more than 99.9% assurance can be given that if this is verified, the circuit will have no delay faults, or in other words, you will be able to get the correct answer in the correct amount of time. So the magnitude of delay caused by the delay fault is such that the new signal value at the output of the NSF block corresponding to the transition at the input or output of the gate under fault is not latched at the state register. It is very, very important. The meaning of the line has to be understood in a very rigorous manner to understand delay fault. Generally, if you have a combinational circuit, there can be delay. That is okay, but mainly we will be focusing on delay of a sequential circuit, because whenever we talk about circuits, mostly they are sequential, and also when you talk about frequency of a circuit, 1 gigahertz, 10 gigahertz, 100 megahertz, that means there is a clock. Whenever there is a clock means the sequential circuit. So whenever we are talking about delay faults and most of the circuits, we are only talking about a sequential circuit. So what it says, we know that in a sequential circuit there is an NSF block, next state function block, it feeds the state registers, there is a feedback, and there is the primary input. Of course, the output function block is there. Already we have seen in the last few lectures that testing the NSF is more difficult compared to the output function block. Once whatever test technology we apply for NSF can be directly applied to the output function block, because it's a combinational circuit. So I mean, we are not much concerned about that because it's more easier to test. Let us again, that's in the same philosophy, let us look at the NSF block. Primary input is the flop and it goes back. So now what happens, this is a combinational cloud. Whatever input you give from the primary input and feedback from the flops, it will take some time before the answer is delivered over here. And we know that there is a clock over here. That is very, very important. The clock will occur at some period and that will decide your speed. You can say that I have designed a 1 gigahertz machine or 1 gigahertz circuit. But then what? The result should also be delivered, keep on changing at the later level of 1 gig. Because say that some inputs apply over here at this clock pulse. Before the arrival of the second rising edge of the clock, this data should be available over here, because then only whatever computation you start giving at this clock pulse, it will be latched by this flip flop at the second clock edge. So before that, this 1 gigahertz, that is the time, that is the frequency, at that level this circuit should perform the job and the data should be delivered. Maybe the circuit is slightly slower, then you can say now I cannot operate at 1 gigahertz, maybe I will operate at 500 megahertz or something lower. Then in that case you will have a more delayed clock, sorry, duty cycle is 50%, you have a more delayed clock, same thing, but in this case the time period will be, in this case the time period will be larger, in this case the time period is corresponding to 1 gig, maybe this is time case is corresponding to 500 megahertz. The frequency, you are reducing the frequency, increasing the time period. So your NSF block will get more time to deliver the result. So even if it is slower, you can get the correct answer. But as a matter of fact, you cannot always keep on delaying the clock, because then you will not be able to get the correct answer at the correct time. Maybe for a certain application you require the answers to be coming at 1 gig level, then you cannot compromise on the frequency and may them say that I will be working at 500 megahertz. You cannot do that. In that case you have to ensure that you have to take a proper type of gates, design properly so that your answers get operated at the proper time. Now what is the fault causing the problem? Say you have verified everything, designed properly, you have done all kind of static and dynamic fault simulation, circuit clock simulation, speed timing simulation, everything you have done, and you know that whatever data you give much before this 1 gig level, your answer will be coming out of the NSF block. So you will have enough time to get the data latched by the flops. But due to certain delay faults in this, the answer is getting delayed. So you are not able to get the proper data in the flip flop at the next clock edge. So those type of testings we have to do in delay fault test. Now let us look at the line, this sentence again, and it will make the stuff more clear to you. So there is an NSF, it is feeding the flops. Now what it reads, the magnitude of delay caused by the delay fault. So there is a delay fault. So the data should have been coming at this point, now it is delayed by this, such that the new signal value at the output of the NSF block, this is required and this is the new, which is changed. NSF block corresponding to the transition at the input or output of the gate under float, this is the gate which is causing it, is not latched by the state register. Some gate is causing a delay over here and it is reflected over here, and your clock say arrives basically at this point of time. This is your arrival of the clock edge. This is your first clock edge, in which case you are giving the data over here, and the next clock edge is coming over here, which is after the required time but much before the new value which is coming out because of the delay. Then what is going to happen? Had there been no fault of this gate, your data would have been coming out of the NSF block at this point of time. So you could have easily latched at this point because your clock is coming at this point. But now due to the delay, the result is not coming at this right time, required time or the right time, it is coming here, but by the time the clock has passed and is not going to latch the new data, it is going to latch some stale data. Now let us look at it in a more detailed manner, or in a more using a block diagram model. So if you look at it, so this is the figure, this is the nested function block, this is the output function block, and this is the flip flop set, this is the clock. So assume that there is some gate here which is causing the delay. So now what happens, say some at this clock edge, let me draw this circuit, or the clock basically. So there is a clock something like this. So this is your clock. In this clock some data has come over here, and we require that before the arrival of this clock edge your data should be available over here, because this clock is basically this clock. So at every positive edge, because I think by digital design fundamentals you know that the flops will latch data either the positive edge or the negative edge. In this course, we are all assuming that everything is happening at the positive edge of clock. So now new data has come over here. So whatever was the value over it is processing. Now before the arrival of this clock edge, your data, new data by the new primary inputs and the state register should be available at this point of time, and it should be available somewhere before this. There is something called setup time. So because if you are giving some data right at this point of time, the flops may not be latching it properly. So there is something called setup time. So this is actually called the setup time. Before the setup time of the arrival of the new clock pulse, your data should be ready over here. So if it is ready, then there is no problem. Whenever the clock comes, this data will be latched and coming to this flip flop. So again draw the clock here. So this is your clock over here again, the same clock we are talking about. Now as I told you that before this setup time, so your data should be ready over here. The data was given as input at this clock period. Now let us assume that there is a gate which is a culprit gate which is causing a delay. So again I would want to emphasize that as a design, you have chosen the proper gate by meeting proper timing, like by the design fundamentals which Professor Arnab sir has taught you. You have taken a proper gate and everything was matched, but because of the design fabrication problem, now this gating is having a more amount of delay. So more amount of delay means what? This is your setup time required. Your data will not be ready by this time. It will have certain delay because this gate is having some kind of a delay due to manufacturing defects. Your data will be coming at this point of time. Now what is going to happen? At this point of time, your flip-flop will latch some data, but this is not going to be this data. This is going to be some stale data which will be coming out and recorded the flop. So you will be delivering the answer at the next clock period. Now what will happen? Now if I extrapolate, so what is going to happen? You are going to get the answer at the third clock edge, which will be the delay. So now what happens? This is your first clock pulse, this is your second clock pulse, and this is your third clock pulse. So you have already seen because of your delay of this gate, this data is coming at this point of time. So at this point of time, some data is coming. At the second edge, this flip flop is not latching it. It is latching this data at a stale data. But this data will be latched by this clock period, third clock period. So at the third clock period, your required data will come over here. So we will have a missing of one clock edge or one clock pulse. So you will be delayed by one clock period for the data to come. So in an accumulative manner, you will find out that your answers are all missing your deadlines. So therefore, this is actually the delay fault model, and we have to ensure that is by test planning as well as by the test pattern application that there should not be any kind of delay, and all the delays has to be matched. But again, I cannot do this at the functional level. It will lead to enormous amount of requirement of time. Secondly, as we have already seen, I cannot go for, like if it's a gate, I cannot go for studying the delay of the transistors. I cannot study the delay of the lines or interconnect lines. I'm modeling by the LR and C. So we are going to go to a delay fault model, which simply takes to the fact that none of the lines should have a delay to rise, delay to fall. Similarly, for all the inputs of all the gates should rise in the proper time and fall in the proper time. Of course, if it happens, basically you will always going to get the answer at the proper amount of time. Because by design, so whenever I say that, say maybe there are the two gates required in chain, maybe after there is one gate, and you maybe want the answer by 3 nanoseconds. So of course I will have gates of delay 1, 1 and 1, or maximum I can have a delay of 1.5 nanoseconds. So by 2.5 nanoseconds my answer will be ready. So when I am designing it, I will take care that all the delays are met so that I can get the answer in the proper time. But only because of the fabrication error, this might have become from 1 to 2. So it will lead to a missing of the deadline. So we will just see by the fault model that all the delay to, that means in this case the delay to rise, so delay to fall and delay to rise, all will happen within 1 nanoseconds corresponding to the inputs for this gate. So these things I will verify. If this is tested, then I know that you will always get the answer in 1 nanoseconds for this, similarly for this and similarly for this. Of course, you are always going to get the answer at the level of 2.5 nanoseconds or less, so that you will always meet the deadline of 3 nanoseconds. So that is what is the concept of delay fault testing. So again, what is the limitation of a single stacked fault model? It's a classical fault model, and we do not generally verify the timing correctness. So I should not call it generally, it does not verify the timing correctness. Because if you want to go for timing correctness, you have to apply stacked fault test patterns at a very high rate. But in case of, and again one important thing I have to tell you, that we are always talking about the tester cost. So the testers are also low end as well as high end. For example, a low-end tester will be able to apply patterns say at maximum 500 megahertz, and a very modern tester will be able to apply test patterns at gigahertz level. So of course, if you want to hire a tester of a higher standard or higher speed, you will have to pay more money. So if you want to do just stacked fault testing, so what we do is that we hire a low-end tester and apply test patterns as a slower rate. So therefore, we say that we generally do not want to verify the timing. So just stacked fault, if you want to test, we will have a low speed tester. For slower speed circuit, it was found that stacked fault models cover some of the delay faults also, but does not hold for high speed circuits. So if you say that my circuit will work at 1 megahertz, 100 megahertz, then you need not worry much about your delay faults, because anyway your whatever faults you have, if it is not a permanent fault like stack 0 and stack 1 or the catastrophic fault, this delay fault etc. will may be there, but it will not at all violate your deadline. Maybe you require a delay of, you design a circuit for 10 nanoseconds. Delay of 10 nanoseconds. Even if the fault is there, you will not overshoot 10 nanoseconds. But if you have a gate which is delay you require to be 1 nanoseconds, then due to a failure, it may easily become 1.5 nanoseconds or 2 nanoseconds. But if you have designed a very slow gate, 10 nanoseconds, then even due to failures of the manufacturing process, such delays will not increase. Because last class we have discussed that why the faults are getting inserted during fabrication, because we are always trying to go for a very advanced manufacturing process, even the technology is not matured. So therefore, if you try to fabricate gates with 1 nanoseconds delay, 2 nanoseconds delay, the incoming of the failures during manufacturing is more than if you are compared to a situation where you are designing a very slow gate like 10 nanosecond, 20 nanoseconds gates, the incoming probability of faults are very less, because our technology is more or less matured to design such kind of gates. So therefore, stacked fault models are applicable for slow circuits, but you will not be able to test for delay fault for a high-end high-speed circuits. But circuit for real-time embedded systems, we require correct output and stabilize before the clock edge. That is, before the setup time, the output results will be stabilized. So we require new fault model, which is called the delay fault model, is required. Now again, as we will find out that the complexity of delay fault test is of course will be more higher than static stacked faults, because single test pattern can state a stacked fault, as you have already seen. But in case of delay fault models, we will see that we will have 2 faults and also you have to do it at speed, and finally ATPG algorithms and will be more complex, and of course more number of untestable faults will be there. So this will not going into the details, but mainly we will be looking at how to generate test patterns and how to test stacked or how to state delay faults. That is our main emphasis in the course. So basically certain ideas you should know, that basically what happens, I'll take a figure. So therefore this is a flip flop and there is another flip flop. So a clock is coming over here, and the next clock period, let us assume that the clock comes at T1. So if you assume that the first clock edge comes at T1, then within this next period, that is your period, the next clock edge will come. So whatever computation you have to do within this period, within this by the combinational cloud block, which is the NSF block, should always be completed by this duration. This is like something called the setup time. This is something called the setup time. So everything you have to finish before by this time period. So by period minus setup time. Period minus setup time, that is the time given to this combinational block to complete its job. If it overshoots, then there is high chances that you will not be able to latch the proper data in the proper time, and there will be a delay. So that is your fault. So what is a combinational path? So this is actually your combinational path. Sorry. So this is your combinational path. So what does the combinational path says? Primary input or a clock flip flop through levels or gates ends at the primary output of a clock flip flop. That means it will start from the primary input or the output of one flip flop, and it will end at the beginning of another flip flop. So propagation delay is the gate transition delays, the transmission delays of the interconnects of a path. That is the time amount required for the gates to change their values, as well as the delay path in the wires. Clock period should always be greater than the propositional delay of the fault, as we have seen. Now if this is the clock period, you have to finish your completion of data completion by up time less than that. What is the delay fault? If the propagation delay of a combinational path is greater than the clock period. That is what? That means you are not able to complete the completion by the setup time. So your data may be coming at this, your data may be ready at this, and your data is ready. So you will not be able to latch the proper answer. So this is your delay fault. So this is again representing the same thing. So your signal changes at the input, this is the combinational cloud, and of course this is what is your called transient period, or which you call the setup time. All your values should be stabilized by that time, and then the next edge comes. So before that your data should be stable, or correct data should have come. If you delay this is your setup time. So if anything happens beyond this, you may not be able to latch the proper value. That is actually a delay fault. So now why delay? there are a lot of reasons delay happens, but we are not going to test for all those things because that will actually take enormous amount of test time. So what they are, switching or inertial delay is the interval between the input change and the output change of a gate, that is input to output change, that is the gate delay. So depends on the input capacitance, device characteristics and output capacitance of a gate. So it will depend on the gate characteristics, because we all know that the gates are designed by transistors. Transistors also have an inbuilt stray capacitance. So that will cause the delay of the gates. It also depends on the rise and fall times and states of other inputs, which is called the second order input, because this gate will have this inertial delay because of the input capacitance. But again, output, these are the inputs. There can also be delay from the gate which is previous to that, because this may will be also driven by some primary input or some other gates. So there can be delay of that. So those delay will also be having an impact on this gate, because this gate will have its own delay and it will try to give the proper answer based on the fact that the other gates which is previous to that will give the inputs at the proper time. If that is also delayed, then we can have some more delay of the gate. And approximation, that is fixed rise and fixed fall time, that is we always assume that there will be a steep rise and a steep fall, but actually in fact it is not. So there are a lot of other capacitance and inductive physical effects which is there. So that means what I am trying to say in this slide, there is a lot of physical parameters involved in the causing the gate delays. Similarly, propagation or interconnect delay is the time taking between the gates, because all gates are connected by interconnects and basically they are something kind of a lines which having LRC parameters, that is resistance, inductance, capacitance parameters, which will depend on the length, loading and different type of routing paths taken. If there are vias, if the routing path is long, so it will have more delay and so forth. So those will also basically come into play of the basically comprise of the delay of a path. So again, if you take all these situations, you have a very big problem of the time. So we approximate it saying there is a lumped delay for gate inputs. So we assume that all the gates will have a proper rise time and a proper fall time. So if it is maintained, we assume that you are going to get the answers in the proper time, similar to stacked fault model philosophy. Now a good example to show you all the fact. So for example, this is a circuit and basically we want to decide on the time. Let us not, for the time being, let us just hide the fact that time period is 7. Time period is 7 means something like this, sorry. Time period of 7 means you will have a something like this. This time period is 7. So whatever answer you have to compute by this cloud, because there is a flip flop over here, they have not shown this, and this is the primary inputs. So by 7 clock period, you have to get your answer ready. Now let us see what happens. So whatever number 1, 2, 1, 3, 1, whatever you are looking inside the gates are the say 1 nanosecond delay of the gates. Now say for example, this one transits from 1 to 0, this one also transits from 1 to 0, and this one is C1 is having the value of 0 basically at the time period of 0. It starts. So at 0 time period it becomes 0, B becomes also 0, C is initially there is not an issue, it is always at the level of 0 and it continues. So the flat line. So now you see, so there is a fall. Of course, it is an AND gate. So if it is if it's from it's always 0. So if this line is from 1 to 0, you will also get a fall in the output. But if it is happening at 0, so this one is happening at 2. The fall is happening from 1 to 0 at 2 because the delay of this gate is 2. Similar as the inversion gate. So from 1 to 0, if it falls, of course there will be a rise, inversion, but it will happen at time equal to 1. Done. So now if you look at this gate, so what is this gate is very interesting to observe. So finally what will be the output of this gate? Is an AND gate. So this is a 1 and this one of course is 0, right. So 1 and 0, the output of the AND gate will be 0, that is the final value, but there will be some transients before this. So what is the transients if you look at it? So initially at time period of, this has all happened at time period 1, sorry say at time period 2. So this one is rising at time period 1 and this one is falling at the time period 2. So if you look at it, this line at time period 2, what is going to be the case? At time period 2, if you look at it, the value is actually 1 and this one is falling at the time period of 2, right. So now what happens? And there is a delay of 1 by this gate. So basically it will all happen at 3 plus. So initially if you look at it, the value of this one was a 0, so output value was 0 at this point, because this one is 0, so this one is also 1, sorry the answer was a 1 over here, but this was a 1 and initially this was a 0, so the output of the AND gate was a 0 over here. So initially the AND gate is 0, sorry, the AND gate was 0 initially because of this fact of this line being 0. Now you see, so this is the initial value. Now what will be the value, final value, sorry, what will be the final value? the final value will also be a 0. Initial, again let me just reiterating. So what is the initial value? So the initial value, this one is 1, that is stable value. So initial value 1 means it will be going to be a 0. Of course the value will be 0 over here. What will be the final value? The final value by this cases, this is rising to 1, no problem. But this will be again falling to 0. So this will be 0, 1, it will be again 0. So this is again the stable value. But in between there will be a transition. So what will be the transition and why the transition will be there? And of course when the value will be coming at the level of 3. Because delay of 2, this is delay of 1, so maximum you have to take. So this is 1 and 2, so maximum will be 2 plus 1 delay it will have. So after time period 3, basically is going to be stabilized. So 3 means I am basically 2 plus 1 and 3. This is basically this is a relative one. So basically if I again, I mean I am not going to more complexities. So if you see at certain point of time, this at t equal to 1, this value is equal to 1, and it is falling at time period equal to 2. So for a certain amount of time, if you look at it, both of them will be 1. For a certain fixed period of time, that is at 2 plus 1 delay. So here if you look at it, so at the time period of 1, this one is 1. At the time period 1, this is also is 1, because only at 2 it is falling. So at time period 1, this value is equal to 1. And of course it will be reflected at 2 because of a delay of 2. So you will observe that at time period 2, the delay is actually equal to 2. The value is equal to 1, which is not a stable value. After that what happened? At time period 2 basically, this one will become 0. So at when this one is actually will become equal to 0, that means again it will not be equal to 1, 1, it will be becoming as 1 and a 0. So it will again become 0. So it is 2 plus 1 equal to 3. So at time period 3 you will find out that the value is again becoming 0 at this point, which is the stable value. So if you just analyze this quickly, then you can see for the time period of 2 to 3, it is getting a spike, which is not a correct value. But it will be stabilizing after some point of time. And the stabilization value is equal to 3 because the delay is equal to 1 and the worst case delay between the inputs 2 plus 1 and 3, you are going to get the answer as a 3 over here. Now let us look at the other path. So other part will be more interesting. Same way you can analyze. So now what happens? The other part basically shows that this is 2 equal to 0 and the delay is equal to 3. So that means 2 plus 3, 5. So you are going to get the answer of a 5 equal to 1. The value of the gate, this gate will be output, this gate will be 1 only at the delay of 5. 2 plus 3. So this final value is equal to 1, inversion, because this is 1, so the answer should be, sorry, this answer is 0, that is the final value is 0, so it is an inversion. So you are always going to get the value 1 over here, which is the correct value. But you will have certain delay for getting it because it is 2 plus 3, that is equal to 5. At time period 5 only you are going to get the answer, so 1. Now in this case if you look at it, so here also you are going to have a transition effect. So what will be the value over here? So it will be 3, 1. So total delay will be 3 plus 1, so you will start having delays incremented. So in this case, you will again take the worst case. So this is 3 and plus 1, that is the 4. So after 4 amount of time, the answers will start coming in. Now if you look at it, so in this case at the other parts I am not drawing, this is the stable part of it, you can easily calculate. So if you look at it, it is 3. At the level of 3, the value of this one is actually becoming 0. But at 3, the spurious value is also equal to 3. This is a non-stable value. So at 3, the value is equal to 1. So at 3, we will find the value of this value equal to 1. And here it is 0. Now not yet proper. Now after 3, at 3 it is falling down basically. So what is going to happen? It is spuriously 0. So 3 plus 1 equal to 4, you will find that this value is falling because again 0 plus 0. But again after what happens? At the level of 5, this has again become 1. This part is 1 and this part is always also 0 at that time. But this has now become a 1. So if this has become a 1, then what is the case? At t equal to 5, this is equal to 1, but this is 0 plus 1 delay. At value of 6, it will become a 1 because this one is actually driving this. So if you look at this diagram, it will make whatever I have told you will make this very clear. That this, now you can just think about this. At t equal to 5, this has become 1. At t equal to 5, this guy is 0, stabilized, and therefore this one is reflected here as 1 at the time 5 plus 1 equal to 6. So at 6 you are going to get the value of 1, which is the proper and stable value. But here there are lot of transitions involved. Now what? Now you can see that if I have a time period of 7, I can easily catch the proper value. But if I have got the value of time period as 6, 4, 3 or something like that, I will going to get a wrong value as the output. So you can think that this one is going to have a proper clock period of 7, I have designed a circuit for this. Now by some means, say we are all expecting that your answer should be properly latched by 6 time period, but due to a delay fault, let us assume, if we assume that this is not operating at 4, it has become as 4 or it has become delayed as 5. In this case, what is going to happen? This value will be latched properly only after the time period of 8, only at time period of 8. 2 it will increase because of this path. So you are going to get a wrong result. So what this example has shown you, you have to analyze this properly, because I have just told you, you also need to do your pen and paper work, then only you will be able to understand properly what is happening. But you can easily figure out that there is always an impact of the clock, because all the outputs are shifted by the delay involved in this. But properly we know, because while designing we know this is guaranteeing 1 nanosecond, this is guaranteeing 1 nanosecond, 3 nanosecond, 1 nanosecond, and accordingly we have calculated the output will be stabilized by 6 nanoseconds. So we have designed a circuit with a period delay of 7. But due to manufacturing problem, this may have becoming 5. But of course, if you think that, we can also analyze what happens if this becomes 2. Will it affect my output? I think it will not, because we have to always consider the worst case. Those things you have to analyze. Okay, so just you need to analyze and find out what is going to happen, that if this becomes delay 2. But definitely if this 3 becomes 5, then basically obviously you are going to get a wrong answer if you latch at 7. So we have to find out that all the gates are having a proper rise to delay and fall delay, so that always you are going to get the answer at the time second, for which your circuit is designed. Because all these transient analysis, all these delays analysis will be done based on the guarantee which is given by the gates. But after manufacturing, certain gates may have more delays, which you have to find out in testing. So this is what is the example. This is the entire timing diagram which corresponds to this circuit. So already I have explained you this timing diagram in words and by making proper mappings and trying the explanation of what time it is falling and what time it is rising, what are these Fourier values, etc. It is your job now to take a print and match these two, that whether they are matching properly or not. Now, just giving you an idea that whenever I say that E is having an impact on the rising edge of F. So basically E is having an effect on the rising edge of F. So if there is a rise over here, so there will be actually also a rise over here. That is actually the impact. So you can see that this rise is having an impact over here by this rise. So this way the whole timing diagram can be analyzed. So again, so this one is having, this rise is having an impact on this rise. So this way you have to analyze the whole timing diagram. Anyway, I have explained you this. Now we are coming to our main job, that is how to test and how to generate test patterns for a delay fault model. So we will be taking a simple example, like faults can be in all the lines, like all the lines you take over here, you have to consider delay to rise and delay to fall. So we are going to take a single fault and try to see how test patterns can be generated and what you have to do, etc. So let us assume that in this gate we are going to assume a delay to rise fault. So this is the rising time, we assume that it will be delayed so that the value will not be latched. So we have to assume that this delay is so much that it will not be able to properly latch over here. So it will latch a stale data, not the proper data. So that means what? Very simple to analyze, that if it would have been properly gone from 0 to 1, so the value would have been 1. But due to this delay to rise fault, you would be still having a 0. So it is very synonymous to stacked fault. But we have to do this testing at a very high speed, that is proper frequency of the clock we have to do it. We have to execute it in a very fast manner, so that this reflection, that whether it is still stuck at 0 or whether it has gone to 1, has to be reaching over this in the proper frequency. Then only you will be able to know that there is no stacked fault, that means there is no delay, but that has to be done at an extremely fast rate. Again, reiterating, this is very important. So if you just look at this gate, so what we are saying, the delay to rise means some rise delay is there, so that you are not going to latch in a proper fashion. That means, what do you mean by delay to rise? That means this line is stuck at fault, it has not rise properly. So I will be doing stuck at fault testing only, but I have to do it at a very fast rate, because this is not a permanent stuck at 0 fault. Given proper time, it will obviously rise and get the normal value. So I have to do this stacked fault test very fast, because unlike a proper stacked fault, it will not remain stacked fault forever. It will remain stuck at 0 only for a small amount of time, but the small amount of time is enough to miss this clock edge over here. So what we have to do? We have to do this stacked fault test at a very fast rate, or the required clock rate. So then only you will be able to detect. So testing philosophy of delay faults is very similar to stacked fault. Delay to rise fault is stuck at 0, delay to fall fault test is stuck at 1, because you will be stuck over here. But that is, this is delay to rise and this is delay to fall. So delay to fall fault is nothing but your stack at 1, and delay to rise fault is nothing but your stack at 0 fault. I think you can easily appreciate the fact. But you have to be very careful, very careful that you have to do it in a very fast manner, because proper stack at fault means it will be remaining at 0 or at 1 forever. But due to delay, only for a short amount of time, which is but more to miss the clock edge, that delay is there, but after that it will become a normal value. So you have to be very careful while testing it. Now example. So assume that this is a stack at fault, we have to test it. So basically what you have to do, of course you have to apply a means basically what you have to delay to rise. So it is a delay to rise. So initially it will be, of course, and one very important one, when you are testing delay fault, it will be never a single pattern, it will be a 2 pattern, because first you have to ensure that 0 and then you have to quickly make it rise. It's obviously, of course. So first thing is that you have to set in the value, because stack at fault testing is always ensuring that basically you have to it's a single pattern test. If it's a scan chain, there will be scan value and the input pattern to test it. But in case of delay fault, very obviously you require 2 patterns, because I first stack 0, then you quickly make it rise and see whether it happened. Delay to fault means you have to make it 1 and quickly make it answer to be 0 and see that whether it can be done in a proper amount of time. So of course 2 patterns are required. So here we are testing the delay to rise fault. So of course first you have to make this line as 0. How we can do it? A equal to 1, B equal to 1, and this is the feedback from the flip flop. So this also is to be 1. NAND gate. So 1 is a NAND gate. So in this case, do not think that these are the delays of these corresponds to delay of the gates, not like that, because this figure and this figure slightly nomenclature difference is there. Here these numbers present the gate delays, but here I am just naming the gates. So if you see, all the gates basically are NAND gates. So to make the NAND gate output equal to 0, you have to put all 1, 1 and 1. So applying A equal to 1, B equal to 1 is very simple, but again this feedback line I have to make as a 1, which we can done by a scan chain. So I am first decoupling the clock, that I am making decoupling the circuit from the flip flops, that is by a scan chain. By scan chain actually I will give a 1 over here and I will apply a 1 over here and I will apply a 1 over here. That is the primary inputs. Feedback can be easily done by scan. So this I am not shown over here, this is scan which I can easily do that. I can make it as a 1. So you are going to get the answer as a 0 over here. This is very simple. Now the concept of delay is coming. So initially this is very slow. Where I am setting this value to stack at 0, I am going to test this rise fault. So I have to make this as a 0. For this I don't require any speed. The speed will be only important for here. If it is a delay to fall fault, so setting a 1 is very simple, but this fault we have to do it at speed testing. This is actually called at speed test. But setting the initial value setting is not required to be at speed. So I am applying the scan value in a very simple manner. Next. So this is already 0 because I have put a 0 over here. Now I have to assume that this is a stack at 0 fault over here, because if there is a stack at 0 fault, then only the rise will not happen properly. But again, as I told you, this is a stack at fault. Maybe in case of a delay fault, it's a temporary stack at fault. Given enough amount of time, it will become 1. But I have to do this at a very fast manner. So what I have to do? So these are stack at 0 fault over here. Quickly I have to make this line rise at a very fast rate. Of course, after applying this scan value, I will actually again stop the scan. So it is normal output over here, as you can see. This is again connected to the circuit. So I am going to give a lower edge. This one is actually happening at this clock edge, and it is happening very fast and at speed testing. So if this circuit they have promised to work at 1 gigahertz, this clock will also be at 1 gig, and this pattern is also applied at the 1 gig. So in 1 gig or whatever is required, I am making this line from 1 to 0. So if it lines becomes 1 to 0, as you know that it's a NAND gate, so it has to be quickly rise from 0 to 1. And if it rises within the proper amount of time, then of course your answer will be correct. Just like again a single stack at fault model, we assume only one gate output or input as a fault at one point of time. So when I am testing for gate number 1, 2, 3 and 4 are assumed to have no delay or stack at faults. So I am making this from 1 to 0. Immediately it should rise from 0 to 1 within the proper delay. So now that is simply I am going to apply a 1 over here. So it just tests that there is no stack at delay fault, but I am doing it at an extremely fast rate. And again I am going to latch this value at the next clock edge. Unlike a simple stack at fault, I will not wait for indefinite amount of time to wait for the results. Because if I wait for indefinite amount of time, this will definitely, maybe if not fast, definitely it will take a very long time and it will rise. So I will not be able to catch this delay fault. So I will immediately use this clock edge to capture the value over here. So that if the stack at 0 is there and it does not give the correct answer by this amount of time, I will say that it is a delay to rise fault. Maybe if I allow 10 more clock pulses to go, this will of course become a 1 and I am going to get the correct answer. So there is not a stack at proper fault. that is static stacked fault is not there, but it's a delay fault. So similarly to stacked 0 fault, but it is for a very small amount of time, and I have to detect it at that small amount of time. So again, so what happened, I am making a very fast rate one, rate this at this time period, and so I have to expect this, that it will be rising from 0 to 1 at a very fast rate. So stacked 0, so this answer is D, that algebra is same, that normal case it is a 1, fault case it will be a 0. B, I am again keeping it as 1. So this is basically your output propagation part. And of course, if this is a 0, so this is also a 0 by this fact, because I am assuming that the gate 2 or this line do not have any delay faults. So basically this 0 is immediately reflected over here, and of course, so whenever any of the inputs of the NAND gate is a 0, you know that it is a 1. So even if this path is having a delay fault, but basically because of, we are assuming that gate 2 is fine, no delay, and this 0 basically will be making it 1 at the proper amount of time. So now basically we are now again this gate number, sorry. So if you look at it, so this is a value of a 1 over here, and this path basically is following as a D prime. So because of this controllability path, so this I am putting a 1, so D prime will be coming over here. Similarly, this is a 1 over here, and this is a D prime, so this is the propagation path, because of the inversion it will become a D. So D means what? It's a normal 0 and fault equal to 1. So at this clock edge, I am going to take this value. So what should happen before the arrival of this clock pulse? This D should appear at G. That means what? So this output, if you think at this clock edge, then if you think this is the clock edge, then the output at G is D. That is, it should become 1 much before this setup time of this. If this is the case, that your G becomes 1 much before the arrival of this clock edge, which is at 1 gig, that is this clock edge, so you are know that there is no delay fault at this. But if there is a delay, that is, if this edge is not coming over here, there is a delay, so it may be delayed by this amount of time, then you know that I will not be able to capture a 1, I will capture a 0 at G, then you know that this was definitely a delay fault. So next what we do, we try, this picture shows this. So basically we are trying to capture the D over here, okay, and absolutely at this clock period, and then your value should be coming over here as properly latched. So if this phenomena, this rise actually happens somewhat before the setup time, then there is no delay over here, and you would have captured the right thing. But if there is a delay over this, you are going to capture this 0, because the rise may be happening over here, this may be happening over here. At this point of time, you will be basically catching a 0 over here, and in this case you are going to get a 0 over here. So in that case there will be a delay fault. But if of course everything is proper, there is no delay fault, then you are going to get this proper latching, you are going to get the answer at this point of time, which is 1, and you know that there is no delay fault, and this test is to be proper. Now this has been latched, so only these 2 clock I have to apply in proper frequency. First you have to give at 1 gig, answer you have to capture at the next clock page. This is actually a proper 1 gig clock, which is the clock frequency of the test of the design of the circuit. And then when this value has been latched, again you have to decouple the froths from the circuit, and you have to put out the output whatever you have latched to the scan. This can be again at a slow speed. So after you have checked for this, you set the scan chain and bring out this value. This you can do at a very slow speed of time, because anyway this value has just to be read. So if you are getting the value of 1, so it is no problem, no delay was there, and if you get the value of 0 over here, so it's at the output it is 0, so know that there was a delay to rise fault over here. So this is how basically we go for testing of delay faults in case of circuits. So what is it? It is very similar, the algorithm is very simple. So what you do, just like this is very simple, just like our stacked, this is the ATPG is very simple, just like for our normal combinational circuits. So if it is a delay to rise fault, first you have to set this to value, set this value to 0, that is the first test pattern. Second pattern is that you have to just test for a stacked 0 fault over here, but this you have to do at a high speed of clock. So it is just like combinational circuit testing, but only one more step is extra is required, that you have to, if it is a 0 to rise, delay to rise, then you have to first set it to 0, and then basically you have to check for a stacked fault. If it is a delay to fault, then basically you have to apply a 1 over here, and in the next clock pulse at speed you have to find out whether it is actually falling from 1 to 0, that is you have to take for a stacked fault. So 2 test patterns are required, so the complexity is just somewhat doubled than the normal combinational or sequential circuit testing. But only thing is that you have to use a high speed tester, because you have to apply these 2 clock pulses at a very high frequency. But again you have to note that the first phase, in which case you are setting this value, and at the same time, at the time when you are proving this value of the output of the scan chain, so reading the value, setting this value and reading the final value, they can be done at a slower clock speed. Only this change and this latching of this change over here has to be done at speed. So two test vectors have to be applied at a very high speed and you have to check the output. But setting the value here and after latching the value, moving it to the output can be done at a slower speed. So algorithm is more or less very similar to our normal scan chain based testing, that is, but only one more step is required where you have to set the lines properly. So that is very simple. Setting the line properly means it is just sensitizing the line and justifying it. Say the absolute test pattern is sensitizing, propagating and basically is justifying. So the same ATPG algorithms we have done can be very easily with very slight modification can be applied over here. But only one thing you have to observe is that two test patterns are required and you really require a high speed tester to test it. That actually increases this cost because algorithmic complexity and test pattern generation complexity is not much higher, but of course it is just double because in case of stacked faults basically you have to test for a single pattern and here you have to apply for two patterns. So maybe twice the amount of time you require to apply the test patterns. So more time in the tester and of course slight increase in complexity of the ATPG algorithms. So you may tell me that okay, I require more time in the tester, that's true, you have to place slightly higher cost, but more of a concern is that you require a high speed tester. That is only actually making it more complex. But one thing you should also understand that when I am testing for a delay to rise fault, of course by default you are testing the stacked. You need not require to test the stacked fault again because of course if your line moves from 0 to 1 at a very high speed, then of course definitely there is no stacked 0 fault. Similarly, if you can assume that it generally at required speed it goes from 1 to 0, so definitely this line does not have any stacked 0 fault. So you can stacked 1 fault, sorry. So you can easily think that I will do bridging, I will go for delay fault testing of all the gates and stacked faults are automatically covered. In fact, you are true. So in fact, if you go for delay fault testing of all the gates, stacked fault models, stacked faults are not required to be tested. So in that way, you can say that I have saved applying some test patterns for the stacked faults. But actually, we will not go by this philosophy. We always try to go for stacked fault testing first, and then we only look at something what is called the critical lines, which has to be tested for delay faults. Like for example, if you look at this circuit, there is one line which is taking 1 to 2 gates to get the answer. There may be delay, all the gates having a delay of 1, you assume. So the delay here is 2. Another part if you look at it is 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. So by this path the delay is equal to 4. Now some people always say that as delay fault testing is very expensive by the tester because you have to apply many high frequency patterns. Because again you have to understand that our tester has lot of channels and it is used by multiple partners. So if you tell that I will just require high speed test patterns for this amount of time, for other parts I will be requiring slow pattern time, it will be a less expensive option. But if you always say that no, I always want to use the high speed channel, so it will be a more expensive option. So what we will try to do is that within the same tester also people want to use the high speed channels less compared to the slow speed channels. So in this case I will only like to test the delay faults for these gates, because if this gate is 1 and 1, this is again 1, 1, 1 and 1, this example. So this is 4 and this is 2. So it is a very rare case that this gate delay will may become from 1 to 5 or something like that. But if any of this gate delay becomes from 1 to 2, because anyhow in this example you are not going to get the answer before how much? 1, 2, 3, 4. Before 4 unit of time you are not going to get the answer from here, because this is something called the critical path. Even if this gate becomes from 1 to 2, if the delay is there, I don't bother. Even if it becomes 3, I don't bother, because 3 plus 1 equal to 4. Of course if it becomes 4 plus, then I have to be worried about it. But in a very if you look at the statistical sense, such a stray case, that is from delay from 1 to 4 will not happen basically. But it is very likely that it may become from 1 to 2. So basically what people will more likely to test is that they will not test this gate or they will not test this path. They will actually test this path. So this is something called a critical path. So whichever is the most time taking path, because everything will be decided by the most critical path or the most part with the most amount of delay. So people will find out selectively some kind of this critical path and they will go for delay fault testing only on these parts, because delay fault testing is expensive, because you have to apply test patterns at a very high speed. But again, for those paths where you have done the delay path testing, you need not go for any kind of stacked fault testing, because as you have shown, delay fault testing automatically covers stacked faults. So we will not be going for any kind of test of stacked fault in these lines. Of course for these gates we will go going for the stacked fault testing and we will not go for any kind of delay fault testing. So even if as we have seen, so even if you have seen that basically delay fault testing can cover stacked faults, but it did not mean that we'll totally throw away the stacked fault model and apply delay fault at all the gates. Rather, we'll apply delay fault test only at the critical path. For all other cases, we'll go for the stacked fault testing only. So the good analysis we have seen over is that delay fault model is a very powerful model, covers many other fault models, but generally it is more expensive to apply. So we'll take care of very critical paths, very important paths which are more dependent on your speed of your operation of your embedded systems. We will be mainly testing those gates in those lines only, and for others the stacked fault always is there. So with this we come to the end of this lecture on delay fault model, which is very important for real time embedded systems. In the next class we will try to again discuss on some more important testing methods which have arisen for modern day deep submicron embedded system design, like built-in self test, fault tolerance, etc. Thank you.